but a buffer solution can kind of stay in a certain pH range with the addition of either. So you just throw in some H pluses. What is it going to react with? What in there does it like? Hey, pretty close to your pKa, right? Pretty close to it. We're just going to alter it a little bit because we happen to have more base in the solution than we have acid. Now, I don't want you to be afraid of buffers. I mean, if you talk to chemistry students who have taken Gen Chem, AP Chem, they may start to shake if you say the word buffer. But I don't want you to fear them. You can do this. It's not that complicated. So first of all, the word buffer just means to cushion or lessen the blow. So a buffer solution is one that actually resists a change in pH. It'll hold its pH pretty close to what it was when you add either acid or base. Typically, if you add acid, you'd expect pH to drop off. If you add base, you'd expect the pH to go way up. But a buffer solution can kind of stay in a certain pH range with the addition of either. So how does this work? Well, a buffer solution, there's a couple ways to make them. One, you're going to take a weak acid and its conjugate base or salt. So for example, hydrofluoric acid, and then his salt would be fluoride. So maybe like sodium fluoride would be a good way to add the conjugate base. So a weak base, here's an example. We've got maybe ammonia and then ammonium, something like ammonium chloride would be a good way to add the conjugate acid. So what makes, how does a buffer solution work? Well, here's an example of a classic buffer solution. If I have acetic acid, that brings, well, some of it stays together as the acid, and then some of it is going to dissociate into the hydrogen ion and then the salt. Well, sodium acetate is going to bring with it sodium ions and then acetate ions. So if you add H+, okay, to this solution, you just throw in some H pluses, what is it going to react with? What in there does it like? Well, it's going to go and take care of it's going to react with the conjugate base. So we're going to be gobbling up some of those. If we add hydroxide to the solution, let's say we added OH, what's it going to be looking for? The OH is going to go grab the hydrogen ions. It's going to attack the acid. So the H plus is going to go get the conjugate base. The hydroxide is going to get the hydrogen ions. And that would keep the pH of the solution fairly steady. Now, a good buffer solution, a very strong buffer solution, what we would call ideal, has large amounts of the acid and the conjugate base. And an ideal ratio would be close to 1. And I'll show you why that's so magical. Here is the Henderson-Hasselbach equation, and it is the basically a function of the pKa. Remember, the pKa is the negative log of the Ka. And then we're going to take the log of this ratio right here. Now, what if that ratio of concentrations was equal to 1? What is the log of 1? It is 0, right? And so it's not going to impact the pH. The pH will be equal to the pKa. So that is a hint right there. So remember, if that ratio is 1, the pH equals the pKa. All right, here is a good example problem. If we have to find the pH, we're going to use our Henderson-Hasselbach equation. So the pH is equal to the negative log of the Ka. And so negative log of 1.8, 10 to the minus fourth. And then we're going to add the log of the ratio of the concentrations. Now be really careful. What goes on the top? The conjugate base, okay, which is my salt right here. And so this guy is 0.25 molar. And then on the bottom is my acid, 0.15 molar. So what's the log of that ratio? Well, the log of that ratio is a positive 0.22. The negative log of the Ka is 3.74. And so they're going to add together to 3.96. Okay, so the pH of a buffer solution is going to be, hey, pretty close to your pKa, right? Pretty close to it. We're just going to alter it a little bit because we happen to have more base in the solution than we have acid. All right, let's look at another equation, problem, sorry. This time, I want to show you this one. This is going to be a little bit of work because anytime you are given concentration and volume, what are you going to have to do? You're going to have to get moles. So we're going to take our acid solution and we're going to add to it some concentration of salt. And so when we add these up, right, we've got 50 mils plus 75 mils, we're going to get a total of 125 mils. And so our final volume is going to be 0.125 liters. All right, so we're going to have to adjust the concentration here by that. So what are we going to do? We've got the concentration of acid times its volume. And that's 50 mils. We got to convert that to liters. The base, we've got, let's see, 75 mils of that. Okay, there we go. And then we've got to divide by our new volume, right? 0.125 liters, 0.125 liters. Okay, so our new concentrations of the acid, 0.060 molar and 0.078 molar. So we had to do all that work just to get those two concentrations. Now, what is the pH of the buffer solution? Well, let's just plug them in. We've got the pKa, which is the negative log of the Ka. Hey, Kas are going to be given, or you can go find them in tables. And then let's take the log of our conjugate base. The base goes on top. Make sure you get that one on top. And then the acid goes on the bottom. Okay, and the log of that ratio is going to be positive because the value is bigger than 1. If the denominator was larger, right, that ratio is going to be a fraction, so we'd have a negative value there. So watch your sign on that. And so this is going to be 374. Add 0.11, so the pH of that buffer solution is 3.85. Now, you could be given the pH of the buffer solution and then use this equation here to go backwards and find the concentration of the acid or conjugate base. Okay, or maybe even the Ka. So I'm just going to throw that out there. You might see problems like that in your class.